now again we want to know the bandwidth. And again, bandwidth by definition is this. The bandwidth by definition is this. Say if this is the, let me say this value equal to, let me pick out any number, say this value at here, the curve at this here is, let me say this is C0, okay? So bandwidth of the system is this. We take the 0 divided by square over 2, and or corresponding is at here from here is 3 dB. Okay, so basically the bandwidth is meaning the system power is reduced to half of the original value, or in this decibel unit, basically is 3 dB down from the initial value. Okay, two equivalent identical statements. So here, that one we define, we put the 3 dB and we finding the corresponding omega here. This is called the omega bandwidth BW. Okay, so basically the bandwidth tell us that basically in this way this is called the bandwidth of the systems. As long as we operate, as long as, for example, you choose your omega, if you choose your omega into the bandwidth, then your operation should give you certain reasonable multiplications for the transfer, for control the input. Okay. So for this one, we define our bandwidth. We can calculate. So bandwidth, by definition, is 1/2 of the initial value here. So the 1/2 of the magnitude. Okay. So again, why we take the 1/2, again, we pick up its bandwidth, and by definition is the power reduced to original, the half of the original. So we take the 1/2 here. So from here, we can calculate the U, should be equal to this number here. Okay, it's not that important, but here we can have the certain drawing. The curve is like, yes. Here today I give you another handout. So on the handouts, the first one you pay attention to the left column here, and that is the drawing of the bandwidth curve, and to implement these equations. Okay, so the bandwidth is a function of the zeta. The bandwidth is a function of the. Let me repeat. On the left column here, basically that gives you the bandwidth equations. And on the left column, this curve, and basically give you one example. I believe this system, this curve basically is a Bode plot, and one example, one scenario of this curve. And if you look at this one, because the peak is very small, so for this illustration on the handout, the damping ratio should be close to the 0.0707, 1 of square cube. Okay, so anyhow, I'll give to you. And on this handout, I try to compare what we have learned. And here it's come to the important conclusions here. And for those kind of notes, we we conducted is in the frequency domain. So that means here we introduce x equal to j omega, and then we keep changing the value of frequency omega. And by the way, let me ask you, what is omega means? Before I'm kind of confusing everyone, right? Anyone can answer this question. What is omega? Again, omega is a parameter, right? So that is a number as a designer they can choose. But what that means omega? So again, we can look at using these systems. So if we have a vibration system like this, okay, and this is our degree of freedom, say x of t. What means omega? Omega is this. If we have external loading f of t, if this f of t gives the harmonic excitations, for example, let me pick up any value here, say cosine, that is omega t here. You choose your harmonic excitation frequency. For different value of the omega, you have a different response of x, right? So that omega is this one. The same role, the omega is the excitation frequency to excite the system response. Okay, so for those of you taking vibrations, you can use the harmonic excitation, that concept. Basically, omega is our operation frequencies for this. Okay, so this is the one I try to correlate and compare our time domain analysis to the frequency domain analysis. Okay, so on this column, that is the old stuff, and on right column, that is old story. I think you should have pay attention. That's the time domain information, and that one for the preparation of the final test, and that is important, right? And now we already learned the Bode plot and the certain preliminary information about the frequency domain, then that is the things on the other column here. If you compare this carefully, you can see, for example, here on the handouts, I list the rising time. This rising time is not the same as I gave to you a couple months ago, but this rising time is more precise. And again, the rising time, we have a couple format, and it's not important to pick either one, but the critical part is the rising time is always a function of omega n. And you can see there omega n is in the denominator. Doesn't matter which equation you pick, omega n in rising time is always in the denominator. Okay, and I believe in before the test too, I sent you the email and clarified the 2 or 3 value of the rising time equation. If you remember that one, so you can use that one, and I would say you can pick either one. Okay, you can pick either one, and when I do the grading, I would know how you're thinking. But anyhow, and that's the omega n here, and the other one is this on the bandwidth. The bandwidth omega n multiplied with, you can look at that equation. So from here you can see how can we, basically I just write out the summaries at the bottom here. The one word is this. When omega n is large, then the rising time will be small. Okay, what I mean, the natural frequencies in terms of the second order system, the natural frequency, when the natural frequency is large, that means the system vibrates quicker. The rising time is small. That makes sense, right? If the system oscillates quicker, that means it will have a shorter time to reach its peak, first peak. Okay. And in terms of our time, the frequency domain analysis, when omega n is large, the bandwidth is large. So again, here we have the link between the time domain, frequency domain. That means if you wish your system to be designed to be agile, that means oscillating quicker or response time is short, then you have to design your system such that the bandwidth is large, it's wide. Yes?
So on this, you for your bandwidth, you have 1 minus damping inertia squared.
Yes,
plus
something, something, yes.
And that one has a plus and minus sign. Do we not count the minus or something?
Depends on the, it might have a typo, use this one.
Okay,
Use
so
this
just
one.
the plus?
Yeah, use this one, okay. I believe that the thing should be equal to this one, but they might have a typo, use this one, okay. And so again, if you, that is kind of very important, kind of the takeaway, the take home message. If you wish your system to be agile, and which means respond very quickly, then you have to have your bandwidth be designed in a wider range. Okay, so that means allow the system to take up more higher frequency without sabotaging his gain, which is the gain. Okay, so recently in my research, I've been encountering one problem here. We've been designing the operational amplifier, and that is to amplify the tiny, very weak signal we are going to detect. And we're going to amplify that signal such that computer USB can read the signal, and then we can, from the computer, we can categorize the curve. The signal we're going to detect, we're going to sample, is the highly oscillated signal, and that will be, the oscillation frequency is at the scale of the gigahertz. Okay, so basically that is kind of light signal. And our bandwidth right now, in simulations, one ECE student told me is in terms of that kind of oscillations, and right now our problem is this. This is the desired sampling frequency we want to achieve. That is outside the bandwidth. He dropped me the email saying that. So in this way, if the students, if any people give you such a message, are you able to interpret what that means? I believe right now you can interpret well, right? So that means this one of simply saying our bandwidth is too narrow. So we have to find other way, either finding new the operational amplifier by looking new brain or new kind of things, or we have to redesign our controls. Maybe replace capacitor or replace certain passive components to widen our bandwidth to cover the frequency we want to detect, we want to sample. You get it? Okay, so that is a very quick applications for these things. Okay, so, and this one, I would say this page is very important, and although I say the frequency domain won't be covered in the test, but this will be in terms of your lifelong learning, this page is very critical to you. Okay. So I think that is the majority of the major things I want to give to you. And then that's it. Would you like to have more? And my plan is pretty much our semester will stop here. Okay, and remaining, if we continue into the frequency domain, and I can tell you we're going to apply one major theory we call the argument theory. That is from the complex function analysis. From there, we're going to study the stability again of the system in the frequency domain, and that will take about at least 2 lecture hours to prepare to get ready for that one. So that's the one thing. The second one is for the drawing of the Bode plot, and right now I have shown you the components. Say, I have shown you the drawing of the Bode plot in this form. And say, you know how to draw the Bode plot of the M as equal to this, or M as equal to 1 over S, or M as equal to S plus A, or M as equal to SA. And right now for this case is we learned is omega n squared, S squared plus 2 zeta omega n. Okay, so you have learned individual components like these things, and to draw the Bode plots manually. Should be okay. If I would give you the exercise, you should be able to do it perfectly. And the remaining, you can try is this. If we have a systems like this, MOS is a combination of those terms. Let me make one example. S 1 plus S 1 plus 10 of S, and here 1 plus 100 of S. If we have the functions like this, then how can we manually sketch the Bode plot? Basically, this one is this, and we can utilize component-wise. We can have all the features, and we can compose them to make up this one. Okay, so that's another topic, and I can, if we could, we can deliver this to you. And this one will take about 1 to 2, probably 1 extra hour, and to do a little bit more exercise. But this one won't be critical because here we can use MATLAB code, right? Called the Bode, B-O-D. If you use MATLAB, then you can do the sketching of this kind of things. Okay. So the remaining topic in these chapters, we really want to deliver. I think we'll need another 2 weeks to complete related topics. And even in the frequency domain, we can use the techniques to design for the designing. Using this as one example, if our bandwidth is here, and this is the desired sampling frequency we want to achieve. So in terms of design, we want to increase the bandwidth. That means, let me draw this one in some way. So maybe this will be my desired system. Something like this. So in terms of design, how can you come up with a design system? So this is our omega n squared as plus 2 data omega n. And this is we added up simply another controller here, so we make up this one. So that means we added up a controller, try to recurve the Bode plot such that we have this desired frequency is into our range here. Okay, so how to do it? Will be the same thing like this, and in terms of controller will play something, so that means let me do this certain way. So the controller, for this example, that may be S plus A, S plus B. Then you choose A and choose B, and repeating the drawing of the Bode plot to see if that consulting curve would be something like this one covering. You got the big concept? Okay, so that is the one kind of give you a guideline, and in the future, I believe the control in the industry you should be seeing that very often. So hopefully you provide you certain basic knowledge for you for the future explorations. Yes.
So if you avoid about power consumption, is there any related to?
Yeah. So power consumption, that means, again, one more time. So say this is a controller, and here we have one more thing, and here this one have the this kind of things. So this is our input, and this is our power. Usually we have a saturations. So here in certain operation range, that's a linear, but once we achieve the threshold, we become nonlinear. So for the power things, we have a constraint, and here that is again go to the nonlinear control system. And here we talk about in this class is linear system, right? And that is I defined that at the very beginning. We talk about a classical and linear system. So here we talk about a scenario, is an ideal scenario.
So you can change any power?
No. As long as you remain your operation within the linear range, then your design should be fine. And many times, if your signal is, if you have ideally go to here, then very likely you can try if you put a kind of this in series combination. if one controller will give you the overshoot, the beyond the threshold, then you can put one controller and second controller, one stage, second stage, third stage, kind of tier-wise to lay out the whole thing and make every single stage within their own linear operation range. Then that should be another solution to go ahead. Okay. And most of the time, in my experience, and when doing my thesis, the master thesis, and that time, most of the time we try to not to attack the nonlinear system. That is the things I learned. Because once you go to nonlinear, all these things will be so different. And we can do it, but if we have option not to do it, then for me, I would choose not to do it. So that is the one. Okay, any other questions? So maybe I'm going to dismiss, and I have other meeting on the other side. So our class will stop today, and Friday, the lecture time. So if you have any questions, and if you like to come here, I will be here. Okay, then we can just open the section for your questions. Okay?